Hey guys, Miss Crumpacker here. We are going to get started on our new unit of nuclear chemistry. So grab your packet, something to write with, calculator if you need it, and let's go ahead and get started. All right, so let's talk a little bit about the history of nuclear chemistry. There are several folks that worked with different things. Antoine Becquerel discovered radioactivity in 1896 while working with phosphorescent materials and photographic plates. Various salts gave negative results, and a uranium sample blackened the plate, which you can see in this picture here. He worked with Marie Curie, which we know is a very famous scientist dealing with nuclear chemistry, and her husband Pierre, and their combined efforts were able to get them the Nobel Prize in physics. Marie Curie became the first woman to win a Nobel Prize in any field, and in fact, she won a second one in chemistry, and she isolated the elements radium and polonium. She is one of only two persons ever to win a prize in two different fields. Her death is attributed to the prolonged exposure to radiation from the many years of research with those radioactive elements. So by definition, radioactivity is the particles, commonly called radiation, which are emitted from nuclei as a result of nuclear instability. So this nuclear instability is really what causes something to become radioactive. There are several different types of radiation, alpha, beta, and gamma. We're going to talk about those, as well as a few other types of radiation, but those are the big three. Each one has different levels of object penetration, meaning that they can go through different thicknesses or types of materials. Some can be stopped by very easily, thin sheets of aluminum, where others need several feet of lead to be stopped. Alpha radiation is emitted helium nuclei. So we use the symbol for helium in order to show this particle in a reaction. 2 protons and 2 neutrons are involved, a total mass of 4, and a positive charge of +2. Due to its high mass and high charge, the alpha particles do not travel very far and are not very penetrating. They can't even penetrate through the surface of our skin. So these are really big, heavy, chunky types of particles. I mean, they're still particles, but in terms of the size of any other particle, it is essentially a helium charged nuclei. But it is very common with heavy nuclides when something bigger like uranium or polonium is breaking apart, it might emit these larger particles as well as other things. So here is a picture of that. Uranium is going through radioactive decay and it forms a new element, thorium, and an alpha particle. So this alpha particle is part of that breakdown, okay? The next one we're going to talk about is beta radiation. It is a fast-moving electron that is formed by the decomposition of a neutron of the atom. So the net effect is a neutron basically changes into a proton, okay? And the way that happens, remember, a neutron is neutral charge. So if I turn it into a proton, I have to take away, I have to make it more positive, and I can do that by essentially like removing negative out of it so it's no longer neutral. So a beta particle looks like that. It is an electron with its -1 charge and a mass of 0, because remember, electrons don't have any mass, or not enough that we can calculate it easily. It has a nearly 0 mass, so it's so low that we don't even, it's negligible. It has a negative charge of -1. It penetrates more than alpha particles because it is smaller, but aluminum foil or thin pieces of wood can stop a beta particle. Now, gamma radiation is a little bit more dramatic, I should say. It is electromagnetic radiation, high energy, that is emitted from the nucleus as it changes from an excited state to an energy state. It is often emitted with those alpha and beta particles, those bigger particles, but it has no mass and no electrical charge. It is a high energy photon. So it is extremely penetrating and very dangerous. It is somewhat stopped by several feet of concrete or several inches of lead. So here is showing you the breakdown of thorium into different elements, as well as these different particles and this gamma ray as well. The gamma ray uses this lowercase gamma symbol, but there's sometimes you'll see it written with that little Y looking thing and then 0 and 0. So this is just showing you that different types of particles and what they can penetrate, okay? So because of their small masses, alpha particles are the least penetrating. It shouldn't be small because of their large masses. They are the least penetrating of the three main types of nuclear radiation. Gamma rays have no mass or charge and are the most penetrating. So this should be large. I mean, it's a small mass. It's a mass of 2, right? But in comparison to the others, which have no mass or no mass, you can see. So because of their mass in general, I would say not large. Because of their mass, alpha particles are the least penetrating, so they get stopped fairly easily. Again, this is just showing you the different types of radiation, alpha, beta, and gamma. These symbols are going to be really important for you to be able to know and recognize. You need to know both the Greek letter symbol as well as the particle symbol. So the particle symbol for gamma is going to be the same. You may see it written with the zeros, okay? But it absolutely is vital that you know both sets of symbols, because we're gonna use them. So you want to make sure that you know what is what. All right, so why do we need to know the particle symbol? That is because in a nuclear equation, we need to be able to figure out what particle or what type of radiation is being emitted by that radioactive element. So here we have several different elements, and we know that they're going through some kind of decay because of what is showing. So the way we do this is we look at these top numbers. Okay, so this is your mass, and this is your atomic number slash protons charge. Because remember, your atomic number is your proton number, okay? So what we need to do is we need to make both sides equal. So all of the mass numbers need to be equal on each side of the arrow, and all of the atomic numbers need to be equal on each side of the arrow. Then that atomic number is going to tell us what symbol to put with those other two numbers. So number 1 has 60 for the mass on the reactant side, and I already have 60, so I need 60 for my products. So I already have 60, which means I don't need any more mass. I have 27 for my atomic number, but on my product side, I have 28. So I need 27. So I need to take away 1. Okay. Well, 0 and -1, that is the charge of the electron. Okay. Which means that this is a beta particle. So the next one, I have 241 for my reactant side. And then I already have 237. So let's see, 241, and then I already have 237. So I need to see what that difference is. So you subtract the 2 and you get 4. So I have a mass of 4, and then 95 and 93, if I subtract those, I get 2. Well, the symbol that is 4 and 2 is helium. So this is our alpha particle, okay? So the next one, we're gonna actually need a periodic table for, because if you notice, they give us a particle here, but we need to know what's gonna go in that blank. So 230 is what I need. I have 4, so 230 minus 4 gives me 226. Now the 226 is not going to tell me what I need. It's going to be the other number. So 90 is what I need for my atomic number or proton charge. And so 2 is what I already have. So I need, 90 minus 2, which is 88. So this is going to tell me my element. Okay, so 88 is element radium. So I'm just going to write the symbol RA. All right, next one. Now, there are times where you can, go back to number 3. This is our alpha particle because of this guy. Okay. All right, so the next one is going to be a reactant, but it can still be a particle. We can have something be part of a reaction that then causes something else to form. So here I have a mass of 14 on the reactant side and a mass of 14 on the product side. So they already equal, which means that my mass is 0. I'm starting with 7 and I go to 6. Well, how do I do that? I subtract 1. Okay. Well, 0 and -1, that's E. Okay. Which we know as a beta particle. This is also called electron capture. Okay, so they are capturing a beta particle in order to form a new element, and that also happens. All right, I think my animations are going to come in here. Okay, so we have talked about the different particles, and we've talked about how those show up in a nuclear reaction. So nuclear reactions begin with unstable isotopes, also called radioisotopes. So those unstable isotopes need to be stable. So it is determined by the ratio of protons to neutrons. Now, if my ratio is equal, so the same number of protons as neutrons, then I have usually a pretty stable nucleus. It's when they start to become off, I get more neutrons than protons or vice versa, that I tend to have some instability. And there's kind of a rhyme or reason, but not really, to that. An unstable nucleus will lose energy by spontaneously emitting radiation. This spontaneous emission is radioactivity. Okay. And spontaneous means it happens on its own. So it's just gonna happen. There's no stopping it. All right. So here is a little bit of what we can predict to have stable or unstable nuclei. So all nuclei or elements with atomic numbers greater than or equal to 83 are unstable. So everything from 83 on is considered unstable. So 83 is bismuth. And so everything after bismuth is considered an unstable nuclei. Nuclei with atomic numbers from 1 to 20 are pretty stable as long as my ratio is 1. Atomic numbers greater than 20 are stable when the ratio is greater than 1. And then even number of protons and neutrons are more stable than those with odd numbers. Okay, so that's just the trend of what is stable. These first 2 points are probably going to be the most important ones for you to be able to identify whether something is stable or unstable. So this is just showing you the number of protons relative to the type of decay that it goes through. You'll notice that, kind of early in this graph, they're stable. So the black line, the black kind of dotted line in the middle is our stable nuclei. So once it gets a little bit past that stable nuclei point is when we start to see a lot more types of decay happening. All right, so plutonium, would it be stable or unstable? So plutonium is the symbol Pu. It is element number 94. So it has 94 is its atomic number. So is it stable or unstable? Hopefully you said unstable because it is higher than element 88. And this is because it is beyond element 88. Okay. All right. So, I don't know why this is not erasing. Let me erase it for you. So when nuclear power was first developed, there were different ways that people would protect themselves from nuclear blasts. They were nuclear energy and nuclear bombs and things like that were really kind of scary during the Cold War era. And so the, government bodies and things like that put out different things to help people try to calm their fears. So some of it was they could protect themselves by hiding in basements or by doing what was called ducking and covering. And we're going to watch this quick little video.
We must be ready every day, all the time, to do the right thing if the atomic bomb explodes. Duck and cover. This family knows what to do, just as your own family should. They know that even a thin cloth helps protect them. Even a newspaper can save you from a bad burn. But the most important thing of all is to duck and cover yourself, especially where your clothes do not cover you.
Remember what to do, friends. Now tell me right out loud. What are you supposed to do when you see the flash? Duck and cover. Duck and cover. Duck.
All right, so was that a correct assumption? No, that was not. Paper and cloth and clothing are definitely not going to protect you from a nuclear blast. Most of our nuclear blasts are going to be emitting not just alpha radiation, they're going to be emitting those gamma rays and things like that. So, you would really need to be in a bomb-proof type shelter, but obviously not lots of people have those. All right, so there are other possible emissions that can happen. A positron emission is simply a electron, but not an electron. It has the mass of an electron, but it has a positive charge. So it looks like an electron, but instead of a negative one, it's a positive one. Sometimes this is referred to as antimatter because it has the same mass but opposite charge of an electron. So it's, antimatter is sort of this idea of, the opposites of what our current existence is, but that's a whole nother topic. Other possible emissions are neutron emissions. So it has the same mass as a proton, but no electrical charge. So basically it's a neutron, which is what we know in the center of our elements or our atoms. This is one way that an unstable nuclei can regain stability is by giving away or removing a neutron. And so that way its ratio is closer to that 1-to-1. All right, so again, these are the other types of radiation in with the first three that we talked about: alpha, beta, positron, gamma, and neutron. Again, these symbol here is going to be really important that you know, because you're going to use those in your nuclear reactions. All right, so if we have new elements, or we want to make new elements, we do that through something that's called nuclear transformation. And it changes those elements into something new. by bombarding them with these particles and getting them to stick. Now, if I take an element that's already stable and I add extra particles to it, it's going to make it somewhat unstable. This is why a lot of our man-made elements are unstable, okay? So it just kind of keep this in mind. Yes, this is how we make new elements, but it makes them unstable. So if I bombard something with alpha particles, I can make new elements as well as other particles, or the same with bombarding with neutrons. I can even maybe take something that was unstable and bombard it with neutrons to try to make it stable and make it a new element if possible. All right, so now that we've talked about the types of particles that can happen and how nuclear instability occurs, we need to talk about how we know whether something is radioactive and how we can kind of classify its radioactivity based on how quickly it decays. So the quicker something decays or breaks apart, the more radioactive it is, the more dangerous it is. And we can do that by calculating the half-life. So basically, half-life is the time required for 1/2 of the radioisotope to emit radiation and decay to its products. And so what happens is the longer something takes to decay, the more stable it is. If it decays in a really fast amount of time, it is very, very unstable and therefore very much more damaging to life. So half-life values can range from anywhere from 2.1 times 10 to the negative 25 seconds. Hydrogen 7 is this, to 2.2 times 10 to the positive 24 years. Tellurium 128 does this. So we can go from fractions of a second to millions of years, billions of years, and that will show us kind of that range of stability. All right, so this is just showing you a graph. At time 0, we're going to have 100% of our original atoms, but after one half-life occurs, whether that one half-life is a matter of seconds or a matter of minutes or hours or whatever, half of those original atoms have decayed into something else, and the other half are still the original atoms. So then after a second half-life, the remaining original atoms have decayed. Half of those have decayed, and the rest are now my new elements, and then so on and so forth. So it's just showing you that everything is dividing in half as we go. There is a calculation that we can do for this, but to me, this can be very confusing. So I'm just going to show you kind of a chart that you can use that seems to be easier to grasp. All right, so nitrogen 13 decays into carbon 13 with a half-life of 10 minutes. How long is 4 half-lives? Well, if 4 half-lives and it's 10 minutes per half-life, then we just multiply by the number of half-lives to get 40 minutes, okay? So this is one example of how we can have you calculate half-life type problems. Let's do another one. If I start with 2 grams of a sample of nitrogen 13, how many grams will remain after 4 half-lives? Notice they didn't tell me how much time, they just told me 4 half-lives. So at time 0, I have 2 grams, okay? And 1 half-life happens, and I have 1 gram because I lose half of it. A second half-life happens, and I lose half of what's left. And I keep dividing in half until I get to 4 half-lives. So after my 4th half-life, I end up with 0.125 grams. So one kind of, I guess, formula you can use, and it's not really a formula, but it kind of is you can have your amount, initial amount, and then you're going to have your half-life occur. So you're going to put your number of half-lives. So 1, 2, 3, 4. And then sometimes you can put the amount of time. So if they had told us one half-life was 10 minutes, we could put 10 minutes under here. Because sometimes they say how much time will have passed and how much is left. Okay, so number of half-lives, amount of time, and then that's going to leave us with our new amount. Okay, and then you would keep going. You would do another half-life, and then the amount of time, and then your new amount. Okay, so this is kind of like your skeleton of what you're going to be doing in order to calculate either amount left over, amount of time that's passed, number of half-lives that have passed. You could do several different avenues of calculations with that little formula. All right, phosphorus 32 has a half-life of 14.3 years. So that's important information. How many grams will remain after 57.2 years from a 4-gram sample? Okay, so there's a couple of ways we can do this. We can use our little chart and figure out what we would start with. We can also figure out the number of half-lives because they've given us a total time and they've given us a half-life time. So if we divide those two, it will tell us the number of half-lives that we go through. So in this case, we go through 4 half-lives. So we're going to start our chart with 4 grams. And then after 1 half-life, we have 2 grams. And after another half-life, we have 1 gram. A third half-life, we have 0.5 grams. And our 4th half-life, we have 25 grams. So we can count that up. Or you can also say, okay, 14.3 years here. Like if you didn't do this top part, you can say 14.3 is 1 half-life plus another 14.3. So this is 28.6 years plus another 14.3 is 42.9 years plus another 14.3 is 57.2 years. So you can do it that way. And that way, if you don't remember to divide, then you can still get the same answer. All right. So with half-life, we have something that's called a decay series. This is a series of nuclear decays that eventually lead to a stable product. So when a nuclei decays, it doesn't always decay just one time. It decays several times and goes through several different changes until it becomes stable. The heaviest nucleide of each decay series is called the parent nucleide. And the nucleides produced by the series are called daughter nucleides. So this is parent nucleide. This is your initial nuclei, your initial elements, so to speak. The daughter nucleides, these are what's made. Okay, made after decay. All right, so this is just showing you the decay series for uranium-238. So the first set of decays it goes through is alpha, and then it turns into thorium. Thorium then goes through beta and gamma, which turns into, what is PA? It's not one I'm super, I don't see it. Must be a new one. Oh, there it is, protactinium. That's a new one. And then it turns into uranium-234, which goes through alpha again and turns back into thorium-230 and so on and so forth until it turns finally into lead. So this is our parent nucleide. Okay. And then everything else are considered daughter nucleides. Okay. All right, so a couple of different ways that we can use these unstable nucleides to our advantage. For example, carbon-14 dating is a unstable particle, or the radioactive particle of carbon, one of them. It is continually produced in the atmosphere when high energy neutrons from the sun collide with nitrogen in the air. And it will combine with oxygen to form carbon dioxide, which is incorporated into plants and living plants and animals. Carbon-14 is continuously replaced. So as long as we're living and breathing, that carbon-14 is going to be constantly replaced in our bodies. After plants and animals die, the carbon-14 is kind of trapped, so to speak. So the amount that you have in your body when you die doesn't change until it starts to decay. So it's going to start decaying and breaking down back through beta emission into nitrogen 14. And the amount that's left when over a certain period of time, the amount of carbon-14 that's left can then allow us to tell how old something is. The proportion of carbon-14 in the atmosphere is relatively constant. And the ratio of carbon-14 to carbon-12 is used to identify the age of things, anything that's organic. It only works on organic materials. The half-life of carbon-14, and this is something I would definitely highlight in my notes, is 5,730 years. So if something is older than that, we could say, let's say something is, 6,000 years old or 5,800 years old, right? So that carbon-14 that is in that substance would have decayed half the amount. And so they can look at the ratio that is left of carbon-14 and compare it to the ratio of carbon-12 that's in that substance, and compare it to say, oh, it's about half of what it should be. So this is X number of years old. All right, so this is just showing you how that happens. There should be a negative sign on there, but this is showing you how carbon-14 breaks down and goes through its half-life. So carbon-14 dating in the Iceman. So this is a individual who is found, and they can look at the current activity per gram of carbon-14, and that it was half of what it should have been if that person were still alive. And so since the half-life of carbon-14 is about 5,700 years, that means that the remains are about 5,700 years old. If carbon-14 is in a sample and only a quarter of it is in the living organism, or only a quarter is in the sample of what is in the living organism, how old is that object? So to go through and have a quarter remaining, that means 2 half-lives have passed. So remember, a quarter is 0.25, and sometimes that helps if you know what the fraction and decimal are. So I go through 2 half-lives, with each half-life being 5,730 years old. That means that object is 11,460 years, approximately. All right, transuranium elements. These are elements that are above 92. If you notice, 92 is uranium. So these are after uranium. They have been found in very limited quantities in nature, but the rest are man-made. All transuranic elements are radioactive. Everything past uranium is radioactive. So these are just showing you some of those elements that are considered radioactive, and the different types of radiation that they may go through. All right, and a particle accelerator, these are where we go and make our new elements. Subatomic particles are accelerated by magnetic fields to travel as close to the speed of light as possible, and then smash into a nucleus. A&M has a small particle accelerator called the cyclotron, sort of like an atomic racetrack. Atoms that are then effectively just smashed together. So this is one of those particle accelerators. Those big circles are actually underground, so they have like roads above it, but there's underground tunnels where these particle accelerators are. All right, so nuclear energy. There are different types of nuclear energy that we can harness. Some of it we can't yet, but we're trying. The first one is nuclear fission. It is the splitting of a heavy nucleus into two nuclei with a smaller mass number. It is used for nuclear energy. So this is showing you a example of the reaction that we do. So basically we take uranium-235 and we bombard it with neutrons. And that bombardment will then break down into two other elements as well as three neutrons. And those three neutrons that are created then continue the process of bouncing into other uranium atoms. So the production of these extra neutrons causes a chain reaction, which has to be controlled. If it's not controlled, we'll talk about what happens. We have experience with this, of these uncontrolled reactions. And so you have to control them, and we'll talk about how we do that. 1 kilogram of uranium-235 is equivalent to 20,000 tons of dynamite. It's a lot. It's a lot of energy. A typical pellet of uranium weighs about 7 grams, and it can generate as much energy as 3.5 barrels of oil, 17,000 cubic feet of natural gas, or 1,780 pounds of coal. So quite a bit of energy stored in such a small little element. So fission is what's used in nuclear reactors, and it does have to be carefully controlled. Much of the energy that is given off is heat. That energy is used, that heat energy is used to produce steam and subsequently goes through a generator to make electricity. A coolant is needed to prevent overheating in the core, and they act as a moderator, which slows down the neutrons so they can be captured by the reactor fuel. Control rods are made of various metals. They are present to absorb excess neutrons and slow down the reaction. They can be raised or lowered into the reactor core. Those control rods are really, really important. So if you need more energy, you can remove some of those control rods to have more reactions. And if you need to slow down or use less energy, you put more in so that there's less chain reactions occurring. So I spoke about how we had experience with uncontrolled chain reactions. Chernobyl nuclear power plant is a prime example of that. It is a reactor that exploded in 86. As a result of the explosion and fire, clouds of radioactive particles were released. The accident caused 31 immediate deaths, and it is an estimated more than 4,000 people were among the approximately 6.6 million of highly exposed and may die from some sort of cancer. However, the Soviet Union still only says that those 31 immediate deaths were directly result of Chernobyl, and they do not attribute many of the others as a result. So this is showing you a picture of that reactor that melted down on that night. We'll talk more a little bit about Chernobyl later on next week. So how did this happen? What went wrong? So if you look on the left, this picture, this is a typical containment reactor. The active fuel core is at the center of that reactor with many feet of shielding and walls, concrete around them. And notice, directly around it is 7.5 feet, followed by then 3.5 feet, followed by a large vapor barrier area, and then another 4-foot and 3-foot containment dome over the top. That way, if something happens, there's a significant amount of protection to try to contain it before it goes south real quick, or before it, so that we can, get people in to do what needs to happen. In Chernobyl, the reactor that melted down, they have 4 reactors in Chernobyl. The number 4 is the one that melted down. If you notice, their reactor has very little things around it. They only had 2-foot concrete walls, and that was only around part of the reactor. The rest of it was just sheet metal, like a normal, like kind of like an old barn, like a sheet metal building, was all they had around it. So when the reactor melted down, they didn't have time. One, it got really hot, and that sheet metal was virtually useless. But then they didn't have enough time to get in there to contain it before those 2-foot concrete walls just sort of melted. All right, so another nuclear disaster that happened, one that y'all probably may remember, is the Fukushima meltdown that happened after the tsunami. So there was an earthquake in 2012, and a tsunami came and flooded the reactors. 3 of the 6 reactors went into meltdown and released radioactive material. There have been no direct deaths due to the short-term radiation. There have been widespread thyroid screening of the 300,000 evacuated persons that were in the area. We won't know the long-term effects of this because it's just, some of this stuff takes years to manifest. But basically the water flooded the basements where the generators were. So when that town lost power, the generators were no longer able to keep the reactors cool. And that was what caused that meltdown. So this is just showing you the damaged reactor units 1, 3, and 4 that were not able to stay cool. All right, so another type of nuclear energy is called nuclear fusion. This is taking 2 lighter nuclei to form a heavier, more stable nucleus. This is how stars make our energy, or make their energy. Extremely high temperatures are necessary in order to initiate fusion. This may be some possible energy source in the future. However, we're not there yet. So this is showing you how we can take 2 light nuclei and smash them together, essentially with a very high amount of heat, to make helium and another neutron. And that would allow a lot of energy to be used in the process. But again, we are not there yet. This is showing you a letter from Albert Einstein to President Roosevelt, talking about the nuclear bombs that came about during World War II. So he was basically writing to the president to explain some of the things that could possibly be a problem with America's supply of uranium and our ability to get that during the wartime. So there was a development of materials during the Manhattan Project. Basically, the project was to become more powerful or to build more powerful weapons before Germany. Germany was defeated in May of 1945. The focus of the project then turned towards Japan, because when Germany surrendered, Japan did not. They continued to fight. So they worked on the project. They were spread all over the country. The main scientific weapons and research and design was done at Los Alamos Laboratory in New Mexico. So in the Manhattan Project, the gadget was detonated in what was called the Trinity test. This is showing you what that cloud looked like 16 microseconds after detonation. If you look at the kind of horizon, see these little black dots? Those are trees, just to give you a little idea of how big this mushroom cloud was. So this is just showing you the chain reaction that happened during that bombing. So after the Trinity test, they came with the 2 nuclear bombs. Little Boy was dropped on Hiroshima in 1945, August 6th of 1945. This is showing you the before and after pictures. So you can see it went from what looked like a normal city to virtually nothing. Everything was kind of wiped out. A Fat Man was dropped on Nagasaki on August 9th, 3 days later, in 1945. Again, this is showing you the before and after. It went from looking like a normal city to virtually nothing. In Hiroshima, approximately 70,000 people were killed as a direct result of the blast, and a similar number were injured. A great many more would later die as a result of nuclear fallout and cancer. Unborn babies died or were born with deformities, and clothing was burned into the skin of survivors. 40,000 people were killed by the bombing at Nagasaki, and about 25,000 were injured. Many thousands more died later from related injuries, radiation sickness of the nuclear fallout. So this is showing you where those cities are in relation to the capital of Tokyo. In 1951, the design for all modern thermonuclear weapons was developed and tested. The US detonated the Castle Bravo device in 1954 on Bikini Atoll in the Pacific Ocean. Castle Bravo remains the most powerful device ever detonated by the US, with a yield equivalent of 15 megatons of TNT. The most powerful artificial explosion on record occurred on October 30th, October 1961, when the Soviet Union detonated the Tsar Bomba. The device had a yield of 50 megatons of TNT and had a blast radius of 22 miles. The Tsar Bomba yield was equivalent to 1,350 to 1,570 times the combined destructive power of Little Man and Little Boy and Fat Man nuclear weapons. So huge. All right, so some of the problems with nuclear radiation, other than the bombs and the devastation that they can cause, is we have nuclear waste, and we don't really have a good way to dispose of it. So after being buried for about 1,000 years, most of the radioactivity will have decayed, but it's got to be buried for 1,000 years. It's a lot. So there are a couple of repositories that can do this in the Yucca Mountains in Nevada. However, getting it there is a problem. So this is just kind of showing you in the Yucca Mountains, they have a cross section of these tunnels where they can put these storage containers deep in the ground. So if you notice, they're about 1,200 feet below the surface or below the Yucca Mountain, but they're only about 800 feet from the water table, which is a little scary. So the problem, though, is getting the nuclear waste to the Yucca Mountains. Many states actually do not allow for the transport of this across their state lines, because if there was some sort of accident, there's no way to contain it. There's no way to get somebody to clean it up. So it's just a very kind of, we have the ability to store it, but nobody will let it get there because they don't want the possibility of an accident occurring. All right, so how do we measure radiation? So we use something called a rad. It's the absorption of 0.01 joules per kilogram of body tissue. A rim is the number of rads, and it is adjusted just for relative effectiveness of the radiation and causing damage to humans. So our background radiation that we get from like the sun and just environmental things is around 0.13 rims per year. A chest x-ray is anywhere from 0.05 to 0.2. As long as you're under 25 rims, there's not usually going to be any detectable damage. It's when you start getting above that that you might have some sort of long-term tissue damage. Ionizing radiation knocks electrons off of some atoms of the bombarded substance to produce ions. Alpha, beta, gamma, and X-rays are things that do this. Cell phones do emit some amounts of non-ionizing radiation, but you can see that, that's still some kind of radiation, right? But it's somewhere around like microwaves. All right, so how do we detect this? We do things like a Geiger counter, which is a gas-filled metal tube that can detect radiation, primarily beta radiation. I can never pronounce this word. Scintillation counter is a specially coded screen to detect radiation. It can detect all types of radiation. And then film badges can also detect beta and gamma radiation. So a lot of times these down at the bottom are worn by people who work in nuclear power plants or work somewhere where there's some sort of nuclear energy occurring. We use radioisotopes in medicine because they can help us check for different things. For example, iodine-131 is used to check for thyroid problems. Radioactive barium is used to check for digestive system problems. Cobalt-60 and cesium-137 are used as radiation sources for cancer treatment. So while there are a lot of scary things that can happen because of radioactivity, like bombs and nuclear meltdowns and things like that, there's actually a lot of really good things that can happen, and a lot of positive things that can come from nuclear chemistry topics. So use in medicine is really, really helpful for identifying if there's problems in your body or to help get rid of things like cancer. Nuclear energy is very clean energy. There is zero emissions. Finding what to do with the leftover products after we've done using and broken down the uranium, that is an issue. But for the most part, it's much cleaner energy than coal energy and natural gas energy and things like that. And as long as you keep your safety precautions in place, you don't have the issues that happened at like Chernobyl. So I hope you enjoyed that. You're going to learn a little bit more as the week progresses about nuclear energy. So go ahead and finish up your notes and turn them in.